Smart Devices Week 101 Introduction to Robotics 1. Can explain the term robotics. Robots in own words answer. Robot. A machine, often programmable by a computer, that can automatically perform complex series of actions. Robotics. The field of technology and science concerned with the design, construction, and application of robots. 2. Can describe briefly the history of robots and provide examples of at least 2 historically important robots. Answer. The history of robots goes back to ancient times with mechanical automata, 4th century BC. Archytas of Tarentum designed the pigeon, a steam-propelled mechanical bird 1495. Leonardo da Vinci designed a mechanical humanoid knight 1921. The term robot was first used in fiction 1972. Waseda University created WABOT-1, the first full-scale humanoid intelligent robot. Examples. 1. Leonardo da Vinci's Mechanical Knight, 1495. A humanoid design capable of sitting up and waving its arms. 2. WABOT-1, 1972. The world's first full-scale humanoid intelligent robot. 3. Knows the origin of the term robot. Answer. The term robot originates from the 1921 play RUR, Rossum's Universal Robots, by the Czech writer Karel Čapek. The word was created by his brother Joseph from the Czech word robota, which means servitude or forced labor. 4. Can categorize robots according to its type. Answer. Robots can be categorized by their locomotion, how they move. Stationary. Cartesian, cylindrical, spherical, SCARA, articulated, parallel-wheeled. Single-wheeled, two-wheeled, three-wheeled, four-wheeled, tracked, legged, bipedal, 2 legs, quadrupedal, 4 legs, hexapod, 6 legs, etc. Swimming, flying, drones, soft robots, snake robots. 5. Can describe in own words the difference between the terms AGV and AMR. Answer. AGV, automated guided vehicle. A dumb vehicle that follows predefined paths, like lines or wires, in a well-defined, static environment with no other actors. AMR, autonomous mobile robot. An intelligent robot that operates in a dynamic environment and can calculate its own path to navigate around obstacles. 6. Can list at least 3 robot usages. Answer. 1. Logistics, transporting goods in warehouses, parcel delivery. 2. Agriculture, spraying crops, harvesting. 3. Search and rescue, reaching dangerous or inaccessible areas to find survivors. Other examples: military, law enforcement, infrastructure inspection, entertainment, healthcare. Week 202 Introduction to ROS 1. Can describe ROS in own words. Answer. ROS, Robot Operating System, is not a traditional operating system, but an open-source robotics framework. It provides a structured communications layer, plumbing, that sits above the host operating systems of a heterogeneous compute cluster, managing message passing between processes, nodes. It also provides tools, libraries, and conventions to simplify creating complex and robust robot behavior. 2. Can describe flexible robotics in own words. Answer. Flexible robotics, in the context of ROS, means the framework is designed to be agnostic to the specified or rigid software capability. It prescribes, requires, little and proscribes, forbids, little, e.g., we don't trap your main, allowing developers maximum flexibility to design their system as they see fit, whether for a single robot or a complex distributed system. 3. Can explain in own words the benefits of using ROS. Answer. Don't reinvent the wheel. Massive amount of shared code and standard interfaces means you don't have veto-right drivers, communication protocols, or common algorithms. Navigation, perception from scratch, fast development. Modular node-based architecture allows for rapid prototyping and testing. Software sharing. Active community and open-source nature make it easy to share and reuse packages. Scalability, suitable for large-scale research and complex projects. 4. Can explain structured communications layer in context of ROS. Answer. It refers to the mechanism ROS uses to enable different parts of a robot, nodes, to talk to each other. Instead of handling process management like a kernel, ROS manages the messaging between these processes, interprocess communication. This layer handles the details of passing data, messages, between nodes, whether they are on the same computer or distributed across a network, treating the system as a heterogeneous compute cluster. 5. Can explain the salient characteristics of and its consequence to ROS. Answer: ROS-1 was originally designed for the PR-2 robot, which led to specific characteristics and consequences. Single robot. Assumed a centralized master. Consequence is single point of failure and difficulty with multi-robot swarms. Workstation class resources. Assumed powerful CPUs. Consequence is it's heavy for small embedded devices. No real-time requirements. Consequence is it's not suitable for hard real-time control tasks. Excellent network connectivity. Assumed reliable wired wireless connection. Consequence is poor performance on lossy networks. Research academia focus. Prioritized flexibility over production hardening. 6. Can describe in own words distributions in context of ROS. Answer: a ROS distribution is a versioned set of ROS packages, like a software release, that are designed to work together. They function similarly to Linux distributions, e.g., Ubuntu releases. Examples include Kinetic Kame, Melodic Mornia, and Noetic Ninjames. They typically follow the release schedule of Ubuntu LTS versions. 7. Can describe in own words different usages of ROS. Answer: robotics research. Testing new algorithms for grasping, navigation, HCI competitions. RoboCup, DARPA challenges, prototyping. Quickly building proof-of-concept robots. Industry, automation, logistics robots, though often requires hardening. Education. Teaching robotics concepts. 8. Can explain the features of ROS. Answer: distributed framework. Nodes can run on different machines, modular nodes. Complex systems broken down into small, interacting processes, language independent. Support C++, Python, Lisp, Java, etc. hardware independent. Standard messages allow swapping sensors actuators easily. Easy testing. Includes powerful simulators, gazebo. Code sharing. Large ecosystem of reusable packages. 9. Can explain in own words distributed systems in the context of ROS. Answer: a distributed system in ROS means the robot brain isn't necessarily one single program on one computer. It is a collection of many separate programs, nodes, that can be running on different processes within the same computer. Multiple different computers connected via a network, e.g., a laptop for processing and a Raspberry Pi for motor control. ROS handles the communication so these parts function as a single coherent system. 10. Can explain the differences between a framework and a library. Answer: library. Your application lives beside the library. You write the main program and call specific functions from the library when you need them. You are in control of the flow. Framework. Your application lives inside the framework. The framework controls the lifecycle, start, stop, loop, and calls your code when specific events happen. Callbacks. ROS is a framework. 11. Can explain interaction of nodes in context of ROS. Answer: a robot system is built as a graph of connected nodes. Each node consists of a specific function, e.g., red laser, plan path, drive motors. They interact by passing messages to each other. Publish-subscribe model. This makes the system robust. If one node crashes, others stay up, and modular. 12. Can describe the downsides of ROS. Answer: slow progression, legacy baggage. Difficult to port old packages to new versions or new OS versions, e.g., stuck on old Ubuntu. Python 3 adoption. ROS-1 was very slow to migrate to Python 3, only fully supported in the final Notebook release. Not real-time. Standard ROS-1 cannot guarantee hard real-time execution. Single point of failure. The ROS master in ROS-1 is a critical bottleneck. If it goes down, communication stops. 13. Can describe the difference between ROS-1 and ROS-2 using the salient characteristics of ROS-1 and Thenu use cases. Answer: ROS-1 was designed for a single, powerful research robot with good network. ROS-2 addresses the limitations to support new use cases, multi-robot teams, removed the centralized master to allow swarms. Small embedded platforms, lighter weight, works on microcontrollers, e.g. micro-ROS, real-time systems, supports real-time capabilities for industrial safety-critical control, non-ideal networks, Uses DDS data distribution service for reliable communication over lossy/Wi-Fi networks. Production environments. More secure and reliable for commercial deployment. ROS Concepts 1. Can describe in own words raw score, master, parameter server, and ROSOut in own words answer. Raw score. The collection of prerequisite nodes and programs that must be running for a ROS system to operate. It starts the master, parameter server, and ROSOut. Master. Provides nomming and registration services to the rest of the nodes in the ROS system. It tracks publishers and subscribers to topics and services. Parameter server. A shared, multivariate dictionary accessible via network APIs. Nodes use this server to store and retrieve parameters at runtime. ROSOut, the standard logging node in ROS. It is the equivalent of stdout/stdare, collecting and logging debug messages from all nodes. 2. Can explain in own words nodes, topics, pub/sub, service client packages in context of ROS answer node. An executable process that performs computation. A system is typically composed of many nodes, e.g., one for laser driver, one for path planning. Package, the main unit for organizing software in ROS. It can contain multiple nodes, libraries, datasets, and configuration files. Topic, a named bus over which nodes exchange messages. Pub/sub, publish, subscribe. A many-to-many, one-way communication model where talker nodes publish messages to a topic, and listener nodes subscribe to that topic to receive them. Service client. A one-to-many, two-way communication model where a client node sends a request to a server node and waits for a reply. 3. Can start list, inspect, and ping existing nodes answer. Start. ROSRun package name node name list. ROSNode list, lists active nodes inspect. ROSNode info/node name. Shows publications, subscriptions, services, etc. Ping. ROSNode ping/node name. Tests connectivity to the node. 4. Can describe the difference in communication characteristics of pub/sub and service client in context of ROS answer. Pub/sub. One way. Data flows from publisher to subscriber. Asynchronous. Publisher doesn't wait for subscriber. Fire and forget. Many-to-many. Multiple publishers and subscribers on one topic. Continuous. Good for data stream censored data. Service/client two-way. Request and reply synchronous. Client usually waits blocks until the server replies like a function call. One-to-many. One server provides service to multiple clients. Discrete. Good for occasional logic requests, e.g., reset simulation. 5. Can explain in own words the ROS architecture on one and multiple computers using schemes. Answer. One computer. The ROS master runs on the computer. All nodes register with the master. Message space between nodes via local loopback or shared memory mechanisms orchestrated by the master. Multiple computers. One computer runs the ROS master. Nodes on all computers must know where the master is via ROS master URI. Nodes register with the master over the network. Once connected, nodes communicate peer-to-peer, directly with each other, sending messages over the network, effectively ignoring the master after the initial lookup. 6. Can explain a complete ROS system from a given scheme answer. Based on common schemes like perception navigation guidance, a complete system consists of interconnected functional blocks, nodes. 1. Perception sensors. Nodes, e.g., laser, EMU, GPS, publish raw sensor data. 2. Processing. Intermediate nodes, e.g., Kalman filter, odometry, subscribe to raw data, process it, and publish refined state estimates, position, obstacles. 3. Navigation planning. A planner node subscribes to the position obstacle map and a goal. It calculates APATH, global local planner, and publishes commands. 4. Control actuation. A driver node subscribes to velocity commands path and sends electrical signals TOTH motors. 7. Can visualize a ROS system as a graph answer. Use the command ROSRun RQT graph. This displays a dynamic graph of the ROS system where ovals, ellipses represent nodes, arrows represent topics, data flow, boxes represent namespaces/groups. 8. Can inspect ROS topics. Answer. ROStopic list. List all active topics. ROStopic info topic. Show message type publishers and subscribers. ROStopic HZ topic. Display the publishing rate frequency, Restopic BW topic. Display bandwidth usage, Restopic type topic. Show the message type used, Restopic echo topic. Print the message data to the screen 9. Can inspect ROS messages answer, ROSMSK show message type. Displays the fields and structure of a ROS message type, e.g. Geometry MSGS/twist shows linear XYZ and angular XYZ. 10. Can plot ROS messages answer. Use the command ROSRun rqtplot. This opens a GUI where you can add topics that publish numerical data to plot their values over time. Navigating the ROS file system 11. Can navigate a ROS system answer. ROS provides specific command line tools to navigate its file system, which can be difficult to do with standard Unix tools due to the deep directory structures. ROSPAC find package name. Returns the absolute path to a package, ROSCT location name /subdir. Changes the current directory to a package or stack folder. E.g. ROSPI, ROSL's location name /subdir. Lists the contents of a package directory directly by name, e.g. ROSPI, creating a Catkin package. 12. Can describe a Catkin workspace in own words answer. A Catkin workspace is a specific directory structure where you modify, build, and install Catkin packages. It is essentially a project folder where all your custom ROS software lives. In the course environment, this is usually at /user/projects/catkin/ws. 13. Can explain the package structure of a Catkin workspace answer. A standard Catkin workspace follows this hierarchy: workspace folder, the root workspace directory, src/source space, where your source code and packages live CMake lists, txt top-level CMake file, symlinked by Catkin package 1/CMake lists, txt build file for this package, XML manifest for this package n/. 14. Can create a package with dependencies inside a Catkin workspace answer. You use the command catkin create pkg inside the src folder of your workspace. Syntax: catkin create pkg package name depend1, depend2. Example: seed /projects/catkin ws/src, catkin create pkg first package std msgs rospi. This creates a folder first package containing package, XML and CMake lists, txt with dependencies onst msgs and rospi. 15. Can inspect the dependencies of a ROS package. Answer: you can use the ROSPAC tool to check dependencies. ROSPAC depends one package. Shows first-order dependencies, direct dependencies listed in thememanifest. ROSPAC depends package. Shows all dependencies recursively indirect dependencies. Rows, publisher and subscriber 16. Can create and run their own ROS publisher using Python answer. Steps to create: 1. Import ROSPI and the message type, e.g. from std msgs, msg import string. 2. Initialize the node, ROSPI, init node name. 3. Create a publisher object, pub equals ROSPI publisher topic name message type qusize equals 10. 4. Loop and publish, pub publish data inside a while not ROSPI is shutdown. Loop often with ROSPI rate. Running 1. Make the script executable, chmod + x my publisher, pi 2. Run with ROSRun my package my publisher, pi 3. Ensure ROScore is running 17. Can create and run their own ROS subscriber using Python answer. Steps to create: 1. Import ROSPI and message type 2. Define a callback function, e.g. def callback data, that handles incoming messages. 3. Initialize the node, ROSPI init node name. 4. Create a subscriber object, ROSPI subscriber topic name message type callback. 5. Keep the node alive to listen, ROSPI spin. Running 1. Make executable, chmod + x my subscriber, pi 2. Run with ROSRun my package my subscriber, pi. Week 3 logging in Python and with ROSPI 18. Can log information using the correct level with the standard logging module answer. In standard Python 1. Import the module, import logging 2. Configure optional but good for files, logging basic config, file name equals myapp, log level equals logging, info 3. Log using levels, logging, debug message. Detailed info for diagnosing problems, logging, info message. Confirmation that things are working, logging warning message. Indication of a potential problem, e.g. disk space low, logging error message. A serious problem, software unable to perform a function, logging. Critical message. Serious error, program may not be able to continue 19. Can log information using the correct level with the ROS logging system answer. In ROS, ROSPI, logging methods match the ROS verbosity levels and are published to /ROSOut. ROSPI, log debug MSG. Information not needed if system is working properly, ROSPI, loginfo MSG. Small amounts of info useful to a user, e.g. node initialized, ROSPI, logwarn MSG. Potentially alarming but expected handled, e.g. using default config, ROSPI, loger, MSG. Serious but recoverable error, e.g. topic timeout, stopping robot, ROSPI, log fatal MSG. Unrecoverable error, e.g. motors caught fire, laser rangefinders and ROS20. Can explain in own words the term laser rangefinders, LiDAR answer. LiDAR stands for light detection and ranging. It is a remote sensing method that uses light in the form of a pulsed laser to measure ranges, distances, to variable targets. A 2D laser scanner is often used in robotics to sense the environment in a 360-degree plane. 21. Can explain in own words how LiDAR work. Standard and solid state, answer. Standard mechanical. Uses a rapidly spinning mirror or rotating sensor head to sweep a laser beam across the environment. It calculates distance using time of flight to F or phase shift techniques. Solid state. Has no moving parts. It typically uses optical phased arrays or fine-tunable liquid crystal to steer the laser beam electronically. This makes them more compact, robust to vibration, and potentially cheaper, wafer-level manufacturing. 22. Can explain in own words the known issues limitations of LiDAR's answer. Lack of visual information. LiDAR gives precise geometry but cannot detect surface properties like color or texture, unlike a camera. It's hard to identifying what an object is, only where it is. Mechanical limitations, legacy. Traditional units are bulky, costly, and fragile due to moving parts, cost. While creating dense data, high-quality LiDARs have historically been the stumbling block in pricing, though solid state is changing this. 23. Can use Python and ROS to read and interpret laser scan data answer. 1. Subscribe. Create a ROSPI, subscriber to the scan topic requiring sensor MSGS/laser scan messages. 2. Callback. In the callback function, access data ranges. This is an array list of distance measurements. 3. Interpret data. Ranges I is the distance at a specific angle. The angle for index I can be calculated. Angle equals data angle min plus I asterisk data. Angle increment. Values can be infinite if out of range. Check for valid data before Math Week 4 simultaneous localization and mapping, SLAM. 24. Can describe in own words the SLAM problem including its components, mapping and localization, answer. Mapping. The robot senses the world from various positions and integrates these measurements to build a model map of the environment. This normally assumes perfect knowledge of the position. Localization. The robot senses the environment, relates readings to a world model, map, and computes its position relative to that map. This normally assumes a perfect map. SLAM, the problem of building a consistent map of an unknown environment while simultaneously determining its location within this map. 25. Can explain the link between SLAM and the chicken egg problem answer. To build an accurate map, the robot needs to know its precise location, motion. To know its precise location, the robot needs an accurate map to reference against. You cannot solve one easily without the other, creating a cycle similar to which came first, the chicken or the egg. 26. Can describe and explain the accumulation of uncertainty in context of sensors answer. Relative sensors, like odometers, measure changes in state, velocity, acceleration. To get position, these measurements are integrated, summed, over time. Every measurement has small errors, noise. Integrating these measurements sums up the errors, uncertainty plus, causing the estimate position to drift further and further from reality as time passes, growing unbounded. 27. Can explain long-term position estimation without a priori information answer. This refers to the goal of SLAM, effectively navigating and knowing where the robot is over a long period in an unknown environment, no prior map. Since relative sensors drift, the robot must use absolute measurements, like detecting a previously visited landmark via loop closure, to correct its accumulated error and maintain a globally referenced position estimate 28. Can describe and explain the accumulation of uncertainty in context of SLAM. Answer: in SLAM, both the robot's pose and the map feature positions have uncertainty. As the robot moves, its pose uncertainty grows due to odometry. When it observes a new landmark, the landmark's position inherits the robot's high uncertainty. This uncertainty correlates everything. If the robot's position is corrected later, e.g., a known landmark, the entire path and map can be retrospectively corrected 29. Can explain Bayes filters in own words and its link with position estimation answer. A Bayes filter is a probabilistic algorithm that continuously calculates the most likely state position off the robot. It works in 2 steps. 1. Prediction. Estimate the new position based on control input / odometry, increasing uncertainty. 2. Update, correction. Refine the estimate using sensor observations of the environment, decreasing uncertainty. 30. Can list 3 types of Bayes filters. How they work is out of scope. Answer: 1. Kalman filter, for linear systems with Gaussian distributions. 2. Extended Kalman filter EKF, for nonlinear systems using local linearization. 3. Particle filter, sequential Monte Carlo, for arbitrary nonlinear distributions, uses many random samples. 31. Can divide localization methods starting from the position acquisition. Answer: localization is divided into relative position measurement and absolute position measurement. Relative: odometry, inertial navigation; absolute: beacons, vision systems, GPS, Wi-Fi, active beacons. 32. Can explain in own words relative and absolute positioning and the difference between them. Answer: relative: estimating position by integrating motion changes from a known start point. It is independent of external references, but suffers from unbounded drift. Error grows with time. Absolute: estimating position by detecting external signals or features, landmarks, satellites. It is independent of previous history and errors do not grow unbounded. 33. Can explain odometry and inertial navigation in context of relative position measurement answer. Odometry uses sensors, like wheel encoders, to count wheel rotations and calculate distance / angle traveled. Inertial navigation uses an EMU accelerometer's gyroscopes to measure acceleration and rotation rate, integrating them twice to get position. Both accumulate error. 34. Can draw a generic scheme of an EMU and explain it in own words answer. An EMU, inertial measurement unit, typically consists of 3 accelerometers, measure linear acceleration in x, y, z. 3 gyroscopes, measure rotational angular velocity around x, y, z, roll, pitch, yaw. Sometimes a magnetometer is added for heading. It provides 6 DOF motion data without needing external references. 35. Can explain beacons and vision systems in context of absolute position measurement answer. Beacons: active transmitters, satellites, Wi-Fi routers, UWB anchors placed in the environment. The robot calculates distance angle to them to triangulate its position. Vision systems: cameras extract visual features, landmarks, from the scene. By recognizing known landmarks or matching scenes to a database map, the robot can deduce its absolute location. 36. Can describe odometry and give an example. Answer: odometry is the use of data from motion sensors to estimate change in position over time. Example: a differential drive robot has rotary encoders on its wheels. If the left encoder counts 100 ticks and the right counts 100 ticks, it moved straight. If left counts 0 and right counts 100, it turned left. The robot calculates its new x, y, theta based on these tick counts. 37. Can explain dead reckoning answer. Dead reckoning is the process of calculating the current position by using a previously determined position, a fix, and advancing that position based on estimated speeds over elapsed time and course, heading. It is essentially navigation without new external reference points. 38. Can explain inertial navigation, including the term IMU answer. Inertial navigation uses a computer and an IMU, inertial measurement unit, to continuously calculate position, orientation, and velocity via dead reckoning. It relies entirely on internal sensors, accelerometers and gyroscopes, and does not need external signals like GPS. 39. Can pinpoint the most significant error source of rotary encoder's answer: wheel slippage. If the wheels spin on slippery ground or loose terrain without the robot moving, the encoders still count ticks, causing the estimated position to inherently diverge from the real position. 40. Can explain drive and other issues with IMU's answer. Drift. Small errors in acceleration measurement are integrated twice. Accel velocity position. A Tanibia's error leads to position error growing quadratically with time, even if standing still. Vibration. Sensitive to mechanical vibrations, motors, bumpy ground. Magnetic interference. If magnetometer is used included, affected by metal electronics. 41. Can explain the link between LiDAR, optical sensors, Wi-Fi, GPS, and absolute positioning measurement. Answer: all these sensors provide absolute positioning data, or data that leads to it. They observe the external world directly to determine location, right now, independent of where the robot thought it was a second ago. They bound the error accumulation of relative sensors. 42. Can explain why Wi-Fi isn't a good sensor in the context of SLAM answer, while useful for rough localization. Wi-Fi is poor for precision SLAM because it relies on signal strength, RSSI, which fluctuates heavily and is affected by walls people. It requires a pre-learned graph map of Wi-Fi signals. It is restricted to areas covered by the Wi-Fi signal. The resolution is typically meters, not the centimeters required for mapping. 43. Can list at least 2 issues with GPS sensors. Answer: 1. Strictly outdoor, cannot work indoors, no line of sight to satellites. 2. Multipath / blocking. Near buildings or trees, signals bounce or are blocked. Urban canyon. Reducing accuracy significantly. 44. Can describe in own words the term visual odometry. VO answer. Visual odometry is the process of estimating the distance traveled and trajectory of a robot by analyzing a sequence of camera images. It tracks the movement of visual features between frames to compute the camera's motion. 45. Can explain the difference between monocular and stereo cameras in context of VO. Answer: monocular, one camera. Hardware is simple, cheap. Cannot natively measure depth, distance. The scale of the map is unknown, dimensionless. You don't know if you moved 1 meter or 1 centimeter without an external reference. Stereo, 2 cameras, simulates human eyes. Can calculate depth directly via triangulation, baseline. Provides a true scale map, but requires higher computation and calibration. 46. Can explain the difference between feature-based and direct method in context of VO. Answer: feature-based. Extracts distinct points, corners, blobs from an image, describes them, descriptors, and tracks only those points between frames. Faster but throws away a lot of pixel data. Direct. Uses the pixel intensity of the entire image or large regions to align frames. More robust in low-texture environments, but computationally heavier and sensitive to light changes. 47. Can describe visual inertial odometry in own words. Answer: VIO fuses visual odometry cameras with inertial navigation IMU. The fast-rate IMU handles rapid movements / shocks where the camera might blur or lose tracking, while the camera corrects the long-term drift off IMU. 48. Can describe a 6-step generic VO algorithm. Answer: 1. Acquire images, get frames from camera S. 2. Image correction, fix lens distortion. 3. Feature detection, find interest points, corners / keypoints. 4. Feature matching tracking, find the same points in the next frame, optical flow. 5. Motion estimation, calculate camera motion, rotation translation from the movement of these points. 6. Optimization. Optional, refine the estimate. 49. Can explain ego motion. Answer: ego motion refers to estimating a camera's, and thus the robot's, 3D motion relative to a rigid scene. It answers: how did I move? Based purely on visual changes in the environment. 50. can explain the benefit of multi-sensor fusion and can draw an example to support the explanation answer. Benefit: combines strengths of different sensors to overcome individual weaknesses. Example: fusing GPS plus EMU. GPS gives absolute position, corrects EMU drift, but is slow 1 Hz and cuts out indoors. EMU is fast, 100 Hz and smooth but drifts. Together, they provide continuous, accurate high-speed position 51. Can explain the basic idea of Markov localization and draw a simple figure to support the explanation answer. It uses a probability distribution, like a histogram, over the grid map to represent where the robot might. 1. Initially, probability is uniform, lost. 2. Robot senses a door. Probability spikes at all locations on the map with doors 3. Robot moves right. The probability humps shift right and blur noise. 4. Robot senses another door. The probability spikes only where the second door matches the movement, distinguishing the true location 52. Can list at least 2 SLAM applications. Answer: 1. Vacuum cleaners, Roomba, mapping a house to clean efficiently without missing spots. 2. Autonomous cars, mapping lanes obstacles to drive safely. 3. AR/VR headsets, mapping the room to place virtual objects on tables. 53. Can describe the difference between interoceptive and exteroceptive sensors and their link with relative or absolute position measurements. Answer: interoceptive, internal, measure internal state, wheel spin, acceleration. They correspond to relative positioning odometry/IMU. Source of drift: exteroceptive, external, measure the outside world, distance to wall, satellite signal. They correspond to absolute or corrective positioning, LiDAR, camera, GPS. Fixes drift. 54. Can explain how acoustic sensors measure distance, where they are applicable, and their shortcomings. Answer: how. Send a sound, chirp, ping, wait for echo. Distance equals time speed of sound /2 time of flight. Applicable: cheap obstacle avoidance, glass detection where lasers fail, underwater sonar. Shortcomings: wide beam, low resolution, slow speed of sound, sensitive to angle reflection, echo can bounce away, susceptible to noise. Crosstalk. 55. And explain how laser rangefinders measure distance, where they are applicable, and their shortcomings. Answer: how. Send light pulse, measure time of flight or phase shift, applicable. Precise mapping, wall following, safety zones. High speed, high accuracy. Shortcomings: historically expensive, heavy mechanical, cannot identify objects, no color, fails angles/mirrors, transparent/reflective. 56. Can explain solid-state laser rangefinders. Answer: LiDARs with no moving parts. They use optical phased arrays to steer the beam electronically. They are smaller, cheaper, robust to vibration, and suited for mass production, e.g., automotive, phones. 57. Can describe how monocular cameras measure distance. Answer: they cannot directly measure distance from a single static image. They can only rely on structure from motion, moving the camera to get parallax, or deep learning estimation. Without movement stereo, scale is ambiguous. 58. Can explain the unknown scale factor issue, including dimensionless maps. Answer: with a single camera, monocular SLAM, you can map the shape of the room perfectly, but you don't know if the room is 1 meter wide or 100 meters wide. The map is dimensionless. All distances are relative to an arbitrary initial unit, e.g., 1 unit equals distance between first 2 keyframes. 59. Can describe a solution for the unknown scale factor issue. Answer: use a sensor with a known metric, stereo camera. Baseline is known, e.g., 10 cm, allowing triangulation of true depth. EMU fusion. Accelerometer measures true meters/second 2 object detection, recognizing an object of known size, e.g., a car or a Coke can. 60. Can describe in own words how stereo cameras work. Answer: 2 cameras are placed side by side with a known distance, baseline. A feature is found in the left image and matched to the right image. The horizontal shift, disparity, indicates depth. Closer objects shift more, distant objects shift less. 61. Can explain the term FPGA. Answer: field programmable gate array. A hardware chip that can be configured, programmed, after manufacturing to perform specific logic tasks very fast. Used in cameras, LiDARs for high-speed processing of emissive data stream, e.g., stereo processing, directly on the sensor. 62. Can describe in own words how RGBD cameras work, including the difference between structured light and time of flight and their shortcomings. Answer: they provide both color RGB and depth D. Structured light, e.g. Connect V1, projects a known dot pattern. Infrared camera looks at how spots deform on objects to calculate depth. Shortcoming: fails in sunlight IR interference. Time of flight, e.g. Connect V2, flashes IR light wall measures return time for each pixel. Shortcoming: fails on reflective transparent surfaces, limited range 63. Can explain the difference between feature maps and occupancy grids. Answer: feature map stores geometric landmarks, points, lines, corners, and their coordinates. Sparse, low memory, susceptible to data association errors. Occupancy grid divides space into a grid of cells. Each cell holds a probability of being occupied or free. Dense, high memory, good for path planning and fusing cheap sensors. 64. Can draw a simple architecture of a SLAM system divided in front-end and back-end. Answer: front-end, sensor abstraction, connects to sensors. Performs feature extraction, tracking, data association, visual odometry. Outputs constraints or pose estimates. Back-end optimization, takes the constraints. Performs loop closure, graph optimization, bundle adjustment. Outputs the globally consistent map and trajectory. 65. Can explain the difference between sparse and dense visual SLAM methods. Answer: sparse uses only a few selected keypoints, corners. Fast creates a point cloud map. Dense uses all most pixels in the image. Computationally heavy, needs GPU, creates a solid 3D surface reconstruction of the world. 66. Can explain the difference between feature-based and direct visual SLAM methods. Answer: feature-based minimizes reprojection error of geometric features, points. Does this point match that point? Direct minimizes photometric error, intensity difference of pixels. Does this pixel's brightness match that pixel? 67. Can describe feature extraction and feature matching in context of visual SLAM methods. Answer: extraction algorithm like SIFT orb finds interesting points, corners, and computes a unique digital fingerprint descriptor for them. Matching, comparing descriptors from frame A to frame B to find the same physical point. Used to calculate how the camera moved. 68. Can explain loop closure in context of SLAM. Answer: the process of recognizing, I have been here before. The robot identifies a previously visited location, often by image matching bag of words. The SLAM system then calculates the error accumulated since the last visit and closes the loop, bending the entire trajectory to make the ends meet, fixing the drift. 69. Can explain why back-end optimization is needed and the difference between camera pose optimization and bundle adjustment. Answer: needed to correct drift and enforce global consistency after loop closure. Pose graph optimization optimizes only the trajectory, robot poses to satisfy constraints. Faster. Bundle adjustment optimizes both the robot poses and the 3D position of every landmark point to minimize total error. Slower, but most accurate. 70. Can list at least 3 SLAM algorithms. Answer: 1. G-mapping, particle filter LiDAR-based 2D. 2. Orb SLAM, visual feature-based monocular/stereo/RGBD. 3. RTAB map, RGBD LiDAR graph-based with loop closure. Others: cartographer Hector SLAM, LSD SLAM, DSO. 71. Can explain semantic SLAM in own words. Answer: instead of just mapping points or obstacles, semantic SLAM uses deep learning to label objects in the map, e.g., chair, table, door. The robot understands the context of the environment, not just the geometry. 72. Can run a G-mapping SLAM with the Turtlebot 3. Answer: 1. Start interaction, start Turtlebot 3 Gazebo World, SH2. Start SLAM node, start Turtlebot 3 G-mapping, SH3. Start Teleup, start Turtlebot 3 Teleup key, SH4. Drive around to fill the map. 5. Save map, ROS run map server, map saver, my map week 5 introduction to drones. 73. Can explain what a drone is in context of robotic smart devices. Answer: a drone is a remote-controlled pilotless aircraft or missile. In the context of smart devices, it refers to an unmanned aerial vehicle that can be autonomous or remotely operated, often equipped with sensors and computing power. 74. Can explain the abbreviations UAV and RPAS. Answer: UAV, Unmanned Aerial Vehicle. Focuses on the vehicle itself. RPAS, Remotely Piloted Aircraft Systems. Emphasizes the entire system, vehicle plus ground station plus communication link, and the presence of a remote pilot. 75. Can layout and taxonomy for UAVs. Drones. Answer: drones are generally categorized by their wing structure. 1. Fixed wing. Like airplanes, efficient for long distances. 2. Multirotor. Like helicopters. Good for hovering and maneuverability. Includes quadcopters, hexacopters, octocopters. 3. Hybrid VTOL, vertical takeoff and landing. Combines fixed wing efficiency with multirotor takeoff/landing, e.g., wingcopter. 76. Can describe why drones became popular during the 2010s. Answer: the popularity exploded due to the drastic reduction in price and weight of electronic components driven by the smartphone industry. This includes cameras, data storage, MEMS sensors, accelerometers/gyroscopes, GPS modules, and efficient batteries. 77. Can categorize UAVs into the corresponding types: fixed wing, multirotor, multicopter, quadcopter, hexacopter, hybrid, VTOL. Answer: fixed wing, rigid wings, requires runway or catapult. High endurance, multirotor, quadcopter, 4 rotors. Most common hobby drone, hexacopter, 6 rotors. More stable, can lift more payload, octocopter, 8 rotors. High payload, redundancy, suitable for cinema cameras. Hybrid, VTOL. Has both wings for forward flight and rotors for vertical takeoff. 78. Can list the different drone usages and provide at least one example per usage. Answer: military. Surveillance, global hawk or combat predator/reaper. Law enforcement. Crowd monitoring, traffic control, accident investigation. Photo and film. Real estate photography, movie shots, perspectives unreachable by helicopter. Entertainment. Light shows, thousands of drones replacing fireworks. Infrastructure inspection. Inspecting wind turbines, power lines, cell towers, or bridges. Search and rescue. Finding missing persons in difficult terrain with thermal cameras. Parcel delivery. Delivering medical supplies, zipline or packages. Amazon Prime Air. Agriculture. Spraying crops, DJI Agras, monitoring crop health. Multispectral. 79. Can explain why drone safety and legislation is a necessity. Answer: to protect 1. Safety, preventing collisions with manned aircraft, near misses, falling on people, property, or causing injuries, propeller cuts. 2. Privacy, preventing unauthorized filming, surveillance of private property or individuals. 3. Security, preventing drones from being used for illegal activities, smuggling, or entering restricted zones, airports, prisons. Drone physics. 80. Can describe the difference between aerostatic and aerodyne aeroplanes. Answer: aerostatic, lighter than air. Uses buoyancy, hot air, helium to float, e.g., hot air balloons, blimps. Aerodyne, heavier than air. Requires dynamic motion through the air to generate lift via wings or rotors, e.g., airplanes, helicopters, drones. 81. Can explain the 4 different forces that exist during flight. Answer: 1. Lift, upward force generated by wings, rotors opposing gravity. 2. Weight, gravity, downward force due to the mass of the aircraft. 3. Thrust, forward force generated by engines, propellers. 4. Drag, air resistance opposing the direction of motion. 82. Can explain the Bernoulli's principle. Answer: Bernoulli's principle states that for a fluid air, an increase in speed occurs simultaneously with a decrease in pressure. Application: wings are curved, airfoil. Air moves faster over the top surface, \, right arrow, \, lower pressure on top. Air moves slower under the bottom, \, right arrow, \, higher pressure on bottom. The pressure difference creates lift. 83. Can describe pitch, roll, and yaw and draw a figure to depict the different axes. Answer: pitch, lateral axis, nose goes up or down. Motion, forward, backward, tilt. Roll, longitudinal axis, one wing goes up, the other down. Motion, sideways tilt movement. Yaw, vertical axis, nose points left or right. Motion, rotating around the center. 84. Understands blade rotation, torque, and tail rotor thrust in context of helicopters. Answer: torque effect, Newton's third law. As the main rotor spins one way, the fuselage wants to spin the opposite way, tail rotor. Provides anti-torque thrust to counteract this spin and keep the helicopter straight. By changing the tail rotor thrust, the pilot controls yaw 85. Understands pitch, roll and yaw in context of helicopters. Answer collective control, lift, changes the pitch angle of all main rotor blades simultaneously. Go up down, cyclic control, pitch roll, changes the pitch angle of blades depending on their position in the rotation, e.g., higher angle at back, lower at front tilts forward. Moves the helicopter forward, back, left, right, pedals yaw, changes the pitch of the tail rotor, rotates the nose left, right 86. Can explain lift, hoovering in context of helicopter's answer. Lift, generated by spinning the rotor blades. Hovering, the state where lift equals weight. The helicopter hangs stationary in the air. The lift force exactly balances gravity 87. Can explain collective pitch rotors, helicopters, and UAVs answer. Collective pitch. The angle of attack of the blades can change while spinning. The motor can run at constant RPM, and lift is controlled by changing the blade angle. Complex mechanics, swashplate, but allows fast response and inverted flight 88. Can explain fixed pitch rotors in context of UAVs answer. Fixed pitch. The angle of the blades is fixed. Lift is controlled solely by changing the speed RPM off the motor. Simpler mechanics, no swashplate. More reliable, cheaper, but slower response time than collective pitch. Commonly used in quadcopters 89. Can explain the different electronic components of an UAV. Autopilot, motors, ground station, GPS antenna, radio telemetry, remote control, battery, buzzer, ESC, electronic speed controllers. Answer autopilot flight controller. The brain, CPU, EMU that stabilizes the drone, ESC. Converts signals from the autopilot into power to drive the brushless motors, GPS. Provides global position for navigation stability, telemetry. Radio link sending data, battery, altitude back to the ground. Remote control receiver. Receives pilot commands, battery, LiPo. Power source, buzzer. Audio feedback, warnings / status. 90. Can explain the modes of motion of a quadcopter and the direction and speed of its rotors. Answer. Layout. 2 motors spin CW, 2 spin CCW cancels torque. Lift hover. All 4 motors speed up equally. Pitch forward, rear motors speed up, front motors slow down, drone tilts forward. Roll right. Left motors speed up, right motors slow down, drone tilts right. Yaw rotate. CW motors speed up, CCW motors slow down, or vice versa. The torque imbalance spins the drone body 91. Can explain the magnitudes of lift answer. Ascend. Lift, weight, hover. Lift equals weight, descend. Lift, weight. Rapid drone software prototyping. PX492. Can describe in own words the PX4 project and its software answer. PX4 is an open-source flight control software stack for drones and unmanned vehicles. It provides a standard, reliable ecosystem for hardware support and autopilot software, used by both hobbyists and industrial companies to build autonomous vehicles. 93. Can explain the term flight controller in own words answer. The flight controller, e.g., Pixhawk, is the onboard computer that acts as the brain of the drone. It reads sensor data, EMU, GPS, and calculates the necessary motor speeds to keep the drone stable and follow commands from pilot or mission. 94. Can list and explain 4 PX4 benefits for developers answer. 1. Modular architecture, flexible, port-based design. 2. Open source, free to use, inspect, and contribute to. 3. Configurability, features are easy to deploy and reconfigure without changing the core. 4. Autonomy stack, built-in computer vision and obstacle avoidance capabilities. 95. Can list and explain 3 PX4 benefits for companies and organizations answer. 1. Safety features, automated failsafes, return to home, and robust flight stack. 2. Permissive license. BSD3 clause allows companies to use and modify the code for commercial products without releasing their secret source code. 3. Validated by real world, used in thousands of commercial systems, ensuring reliability. 96. Can describe in own words MAVLINK, Q ground control, and MAVSC answer. MAVLink. The lightweight messaging protocol used for communication between the drone, ground station, and onboard computers. Q ground control. The application GUI running on a laptop tablet to plan missions, configure the drone, and view video telemetry. MAVSDK. A a set of programming libraries, C++, Python, Java, allowing developers to write code that interacts with the drone via Mavlink Easily 97. Can draw and completely explain the smart UAV architecture. Answer: Flight controller. Handles real-time stability and flying hard real-time. Companion computer, e.g. Jetson/Raspberry Pi connected to flight controller. Handles high-level tasks, AI, image processing, SLAM, 4G comms, Mavlink. Connects flight controller companion computer ground station. Q ground control, the human interface on the ground 98. Can describe in own words the term companion computer. Answer: a separate, more powerful computer onboard the drone, like a Raspberry Pi or NVIDIA Jetson. Dedicated to high-level tasks that require heavy processing, like video analysis, AI, obstacle avoidance, or internet connectivity, which the simple flight controller cannot handle. 99. Can explain in own words the terms. SITL and HITL. Answer: SITL, software in the loop, simulating the entire drone and its environment on a PC. The autopilot code runs on the PC as a program. No real drone hardware used. HITL, hardware in the loop. The actual autopilot hardware, flight controller board, is plugged into the PC. It thinks it is flying, but the sensor data comes from the simulation on the PC 100. Can list 3 benefits of a companion computer. Answer: 1. Computational power. Can run heavy AI computer vision algorithms too. Connectivity. Enables 4G/5G/Wi-Fi cloud connection. 3. Offloading. Keeps the flight controller safe and focused only on keeping the drone in the air, while the companion handles complex logic. 101. Can list 5 factors for selecting a correct companion computer. Answer: 1. Size and weight. Must fit on the drone and not be too heavy. 2. Power consumption. Should not drain the battery too fast. 3. Computational speed. Needs enough CPU, GPU, RAM for the intended task, e.g. AI needs GPU. 4. Interfaces, connectivity ports, USB, Ethernet, UART/serial. 5. Software support, compatibility with OS, Linux, Ubuntu, and libraries, ROS, MAV SDK.